Hello everyone, greetings of the day. I am Dr. Abhijith Bijanu, Assistant Professor, Department of Chemistry at MITS. So today I am going to give you an insight about radiations, its importance, hazards, and how to protect against radiations. So this is the flow of my presentation where I will give you a brief introduction of my slides. What is radiations? What are the importance of radiations? Types of radiations? What are the hazards from radiations? What are the general sources of radiations and how we can protect ourselves from radiations? And at the end, I will briefly summarize everything. So the first question is, what is radiation? Radiation is a wave or subatomic particle that transports energy from one entity to another entity, and depending on the energy, radiations are broadly classified into either ionizing radiations or non-ionizing radiations. So this is the electromagnetic spectrum. We can see that radio wave is the highest wavelength radiation and gamma ray is the lowest wavelength radiation. But when we talk in terms of energy, gamma ray is the highest energy radiation and radio wave is the lowest energy radiations. So as I mentioned earlier, on the basis of energy, radiations are classified into two categories, that is ionizing radiations and non-ionizing radiations. Ionizing radiations are high energy, X-ray, gamma ray and some part of the ultraviolet radiations, and all rest are non-ionizing radiations. Right. So coming to the importance of radiations, today we are surrounded by radiations everywhere. We get sunlight, that is also a form of electromagnetic radiations. We are using mobile phones, laptops, there we are using radio waves. We are using microwave ovens, there also we are using microwave, which is an electromagnetic radiations. So we can say that radiation is an imperative part of our daily life. So these are some of the important applications of both ionizing and non-ionizing radiations. So ionizing radiations can be used for radiation therapy, like for cancer treatment. X-rays are used for diagnostic imaging and CT scanning. Similarly, we are using nuclear industries, nuclear power plants, that is based on ionizing radiations. And some examples of non-ionizing radiations are, we are seeing objects that is based on visible radiations. We are using mobile phones, TV broadcasting, that is based on radio waves. And we are using microwave ovens, that is also a non-ionizing radiations. So we can say that we are using radiations in almost every part of our life, and radiation is very important to us, right? So out of both ionizing and non-ionizing radiations, the ionizing radiations are considered to be hazardous, but not the non-ionizing radiations. So from now we will only delve deeper into the concept of ionizing radiations. So what is an ionizing radiation? Ionizing radiation are those radiation which has enough energy to eject one or more electron from the atom of a material on which it is irradiated, right? So the examples are alpha particles, beta particles, X-ray, gamma ray, and some part of UV radiations, right? So further, the ionizing radiations are categorized into two categories, that is particle radiations and electromagnetic radiations. So the question is, what is particle radiation and electromagnetic radiations? So particle radiation consists of subatomic particles that are in motion carrying energy. These particles have mass and sometimes charge and can interact with the matter. Examples are alpha particles, beta particles, and neutrons. So these are particle ionizing radiations. Now come to electromagnetic ionizing radiations. So what is electromagnetic radiation? It is an energy transmitted through space or matter via oscillating electric and magnetic field which travel as wave. So the examples are X-ray, gamma ray, and some part of the ultraviolet radiations, right? So as I already mentioned, that ionizing radiations are hazardous. Why it is hazardous? Because it causes various diseases like cancer, cardiac problems, cataract, and other acute radiation syndromes like burning, nausea, and vomiting, right? But the question is, why it is hazardous? What is the science behind it? This is a major question. So the answer is, ionizing radiations can ionize the living tissue and break apart them, especially the DNA molecule which contains the genetic informations. They can break the DNA and it will lead to the abnormal reproduction of DNA molecule, and it cause mutation which can ultimately lead to cancer and genetic disorder, right? So that is why these radiations are considered to be hazardous. So what are the general sources of radiations? So mainly we get ionizing radiations from medical uses like in X-ray diagnosis, radiation treatment, or from occupational exposures. Those workers who are working in the nuclear power plants, in hospitals, in the radiology department, they are exposed on a regular basis. then the fallout from nuclear tests, radioactive contaminations from air or water, or radioactive consumer goods, building combustible fuels, excess security system, etc. Apart from these, we get natural background radiations, that is zero point 0.9 millisievert of radiation per year. What is natural background radiation? So the radiation that we get from cosmic rays through space, the radiations we get from terrestrial radiations like from rocks, soils, or also we get natural background radiation from foods like banana, carrot, potato. From these, they contain a very trace amount of radioactive elements. So these are the sources of natural background radiations. So which we get about zero point 0.9 millisievert per year, right? So here we can see that the major source of radiation is natural background radiation, that is 82%. And the rest 18% only is from the man-made source. So out of those 18%, 58% are from medical X-rays, either in the form of X-ray diagnosis, CT scan, or it can be radiation treatment. The next highest is from nuclear medicine, that is 21%, from consumer product, and only 2% from occupational exposure, 2% from fallouts and nuclear fuel cycles. So the question is, we are saying that radiation is harmful, they are hazardous, but up to what limit? So as per the International Commission on Radiological Protection, an adult can be exposed to 20 millisievert per year. If we are getting radiation below than that, we are completely safe, right? So radiations are hazardous, but only after a certain limit. So this data will give us a certain idea of how much radiations we can get, right? So the person who is working in nuclear power plants, they typically receives less than 5 millisievert per year. So those who are medical radiologists and technicians, they get around 1 to 5 millisievert per year. So those workers who are working in research facility, they get around 10 millisievert per year. Or when we go for a CT scan or a chest X-ray, we get around 0.1 millisievert, or in CT scan, we can maximum get about 10 millisievert per year. So we can see that even a worker who is working professionally in nuclear power plants or X-ray related facilities, still they are getting less than 5 to 10 millisievert per year, and the limit is around 20 millisievert per year. So for a journal person, we are getting very less amount of radiation per year, so we should not be afraid of radiations, right? So, but even after getting to know that the radiation are safe, but we should work for its protection, because undesirable exposure or accidental exposure can lead to some hazards, right? So for that, we should follow the ALARA principle. What is ALARA principle? We should get radiation exposure as low as reasonably achievable. So there are three methods in the ALARA principle. First is limiting the work period near the radiating source. We should spend less amount of time near the radiation source. Second is working far away from the radiating source. We should work far as much as possible from the radiation source. Then we will get less radiation dose. And the third is working behind the radiation shielding material, right? So these are the three methods in the ALARA principle. For a person who is working in radiation vicinity, like in medical diagnostic, in nuclear power plants, the first two options are not feasible, right? For them, working behind some shielding material becomes the best practice, right? So what are the appropriate material to shield different kind of radiations? We can see that for shielding alpha radiations, a thin sheet of paper is good enough. For shielding beta radiations, which is penetrating to our body, a thin sheet of aluminum is good enough to shield beta radiations. But for X-ray and gamma ray, we requires thick sheets of lead, right? And for neutrons, it requires water or concrete walls or layer to shield neutron particles, right? So in conclusion, we can say that lead is widely used to shield X-ray and gamma rays, and concretes and waters are used to shield neutrons, right? So here we can see that the real-time applications of radiation shielding materials, like in the first image, we can see that in diagnostic imaging, this patient is wearing some apron that is made of lead. This is a lead lining in an X-ray room. So for making an X-ray room, they are using some lead lining in the walls so that it will not allow the radiation to go outside, so that the people who are staying outside, they will be safe. So in the third image, we can see that the concrete walls are used for making an X-ray room. Very thick concrete walls are used. So in the fourth image, we can see that radiation shielding apparels can be in different forms, like radiation shielding thyroid shield, gonad shield, aprons, skirts, right? In aerospace, the astronauts are wearing some radiation shielding apparels. That also requires some polymers or lead-based materials. Or in the last diagram, we can see that lead sheets are used in different forms to shield X-ray and gamma rays, right? So the question is, why there is a need to replace lead? Because everywhere we are using lead in most of the cases for X-ray and gamma shielding, but there is a problem with lead. What is that problem? Lead is highly toxic in nature, and it is not good for shielding gamma. It is not good for shielding neutrons. It is only good for shielding X-rays and gamma rays, because when the lead particle interacts with the neutron, it generates secondary X-rays and gamma rays. Also, it has very low melting points. So in applications which require higher temperature, in those applications, lead will be melted, right? And there are many reports showing the lead poisoning effects from the past. So these are some of the articles that I have put here, which is showing how much harmful lead is for the mankind. And as per the Comprehensive Environmental Response Compensation and Liability Act, lead comes at the second position among the top 20 most hazardous substance, right? So hence there is a need to develop a material which can replace lead, which is non-toxic and which can effectively shield X-rays and gamma rays. But again, the big question is how to choose that material. What is the science behind it? How it is shielding X-rays, gamma rays, and neutrons, right? So this is the big question. So for that, to understand which material is appropriate for shielding X-rays and gamma rays, we should understand the mechanism of interaction of these radiations with matter, right? So there are three phenomena which govern the shielding of X-ray and gamma ray, that is photoelectric effect, Compton scattering, and pair production. Depending on the energy of the incoming radiations, these phenomena takes place, right? When the energy of incoming radiation is in between 10 kiloelectron volt to 100 kiloelectron volt, then photoelectric effect predominates, and the cross section of interaction through photoelectric effect is directly proportional to Z to the power 4, where Z is the atomic number. So we can say that higher the atomic number, more will be the chances of photoelectric effect. Similarly, when the incoming radiation is having energy 100 kiloelectron volt to 10 mega electron volt, then Compton scattering will predominates, and the cross section of interaction through Compton scattering is directly proportional to Z, right? And when the incoming photon has energy more than 1.02 mega electron volt till 100 mega electron volt, it will interact through pair production, right? And the cross section of interaction through pair production is directly proportional to Z to the power 2. So in all the three phenomena, we can see that the cross section of interaction is proportional to atomic number, right? So higher the atomic number, more will be the shielding. So the two factors that governs the shielding are the material should have higher atomic number, as well as it should have higher density. Higher density will allow the material to interact with the radiation, and high atomic number will lead to higher photoelectric effect, Compton scattering, and pair production. So nowadays, extensive research is going on from last 2 or 3 decades to develop a lead-free, non-toxic radiation shielding material which can effectively shield X-ray and gamma ray. So for that, people are using tungsten because it is having very high density. Now they have started to use bismuth as well, because bismuth is having higher atomic number. Plus they are using iron, tin, and many other metals which are non-toxic in nature, higher density or higher atomic number, right? So to summarize everything, we can say that radiations are of two types depending on their energy, that is ionizing radiations and non-ionizing radiations. Out of these two, ionizing radiations are considered to be hazardous. Why? Because it can break the DNA base pair. It can cause various diseases. So further, the ionizing radiations are categorized into photon and particle radiations. The particle radiations are of two types, that is neutron, alpha particle, and beta particles. And for photon, there are two types, X-ray, gamma ray, and some part of the ultraviolet radiations. To shield alpha and beta particles, thin sheet of paper and aluminum are good enough. To shield gamma ray, X-ray, and neutron, we require proper shielding materials. So this shielding material can be in two forms, either in construction and building materials, or it can be in the wearable protective garment forms, right? So in the wearable protective garments, we are using lead-based composites and polymer composites as radiation shielding materials. And in construction and building material, we are using metallic lead-based materials, concretes with heavy aggregates, and glass materials. So what are the takeaway of this presentation is that we should not be afraid of radiations, because we should rather debunk the misconceptions like all radiations are deadly, right? Rather, radiation is a natural part of our daily life. We are exposed to natural background radiation daily, from cosmic rays, terrestrial radiations, from food, right? Plus, we should follow the ALARA principle. What is that? We should keep the radiation exposure as low as reasonably achievable. We should avoid unnecessary exposure to medical imaging unless prescribed, right? And we should also follow safety standards and regulations exists to ensure safe use of radiations in all fields. Like, there are certain radiation governing bodies like ICRP, NCRP, they have made some regulations and rules. So we should follow those regulations and rule when we are near in the vicinity of radiation sources, right? So these are some of the references that I've used for making this presentation slides. Thank you for your attention. I hope I was able to convey the insights of radiation, its hazards, and how to protect. Looking forward to see you in the next session. Have a great day. Thank you.